This is our fourth module for this SEM and the second one for our midterm. This one is entitled Basic Helicopter Aerodynamics and Performance, and this would be the pretty much the coverage for your second short quiz. So let's begin. So lesson 4, we have these topics, 7 in particular. Let's first start with the basic helicopter aerodynamics. Okay, so we have, I would be just giving you a brief explanation about the helicopter controls. So we have three, namely the collective pitch control, the cyclic pitch control, and the anti-torque pedals. So the collective is used to make changes to the pitch angle of our main rotor blades, and does this simultaneously or collectively from the name itself. Later on, I would be showing you the video para makita nyo yung mga certain movements as to as to which these major controls are responsible. So for the second one, we have the cyclic control. This allows our pilot to fly the helicopter in any direction of travel, whether forward, rearward, left, or right. And lastly, the anti-torque pedals. These are located on the cabin floor, as you may see in the picture. These are controlled by the pilot's feet. This pretty much controls the pitch and therefore yung thrust ng ating tail rotor blades or tinatawag ding or other anti-torque system for that matter. So in addition to these major controls, the pilot must also use what we call the throttle control, which is usually mounted directly to our collective pitch control in order to fly the helicopter too. So to further understand this, here is a video recording I will be playing.
Okay, so there's a total of 4 flight controls the pilot has to worry about. First is the tail rotor pedals, which are operated by both feet, and this is how we turn the aircraft into hover. So if you move full right pedal, you look at the tail rotor and just adjust the pitch of the blades. Full left pedal, and then once we're in forward flight, the pedals basically become neutral because the tail rotor at that point is on for the drive. Second control is called the collective. It's the stick on the left-hand side. We're lifting up on the stick. It adds equal pitch to each rotor blade, which then picks the aircraft up into a hover. And then if you push the stick down, the aircraft comes back down. So this is the up and down control. Next control, third control, is called the cyclic stick, which sits in between your legs. It's controlled with the right hand, and this is basically your direction and speed control. So by moving the control left and right, it's left and right turns. If you want to fly the aircraft forward, you push it forward. If you want to fly the aircraft backward, you pull it backward. So this is your direction control. It's also your speed control. So the further you push this forward, the faster the aircraft goes. The final control is the throttle, which is controlled by the left hand grip. It's like a motorcycle grip. You just twist it, and that controls the engine speed. Those are the flight controls.
Have still under the helicopter controls before we proceed to the aerodynamics proper is the swash plate assembly. So by definition, the purpose of the swash plate is to convert stationary control inputs from the pilot into rotating inputs, which can be connected to the rotor blades or control surfaces. It is basically consisted of two main parts, which is the stationary swash plate and the rotating swash plate. So basically, the control inputs that are made by what I call this our collective and cyclic, these are transferred to the rotor blades. How? By these swash plates. So we have the stationary and rotating nga. So stationary, from the name itself, the non-moving part. These are the parts that are directed by our flight controls. Whereas yung ating rotating swash plate naman, from the name itself, these are the part that moves and responsible for transferring the directed information to our rotor blades. So now we have the freewheeling unit. So the freewheeling unit automatically disengages the engine from the main rotor when engine revolutions per minute or RPM is less than the main rotor RPM. So think of it this way. You have a bicycle and you use the pedals to turn the wheels. But if, for example, you're going down a hill, increasing speed, they may come a point where your wheels are turning your pedals. So technically, we don't want that. We want our pedals to turn our wheels for us to have control. Pag ganun, di ba, we have to stop to regain control sa pedals. That's the idea behind the freewheeling unit. We want the engine to drive the transmission. We don't want the transmission to drive our engine. So it's a pretty simple concept after all. Okay, now we reach the three basic functions of helicopter rotor. The first is generation of vertical lifting force or thrust in opposed to the aircraft weight. The second is the generation of horizontal propulsive force for forward flight. And lastly, the means of generating forces and moments to control the altitude and position of the helicopter. Pretty much same essence siya sa fixed wing, but unlike a fixed wing aircraft where certain roles are divided, all three of these must be supported by the helicopter rotor alone. So, ganun siya kahalaga. So, in order for us to ensure that the rotor can perform these functions, the rotor designer needs to what? Needs to have significant knowledge both of the aerodynamic environment na in which our rotor will work and how the aerodynamic loads could influence the dynamic response of the blade and the overall rotor behavior. So this is pretty much just a recall. So as we recall this, so rotor blade profile. So the main and tail rotor blades of the helicopter are airfoils, and air is forced to pass around the blades by mechanically powered rotation. So this particular topic, the main and tail rotor, we discussed this configuration sa ating module 3. So as you know, according to this statement, main and tail rotor are both airfoils. They have the same profiles. So, as a recall, ano nga ba ang airfoil? So, again, airfoil is any surface producing more lift than drag when passing through the air at a certain angle. So, as we know, airfoils can be either rather symmetric or asymmetric. So, baka lang ma-encounter natin itong terms na to. Two of them are the flight path velocity, which is the speed and direction of the airfoil passing through the air, and syempre yung blade pitch angle natin, which we encountered na during our propeller topics. So, it is pretty much the angle between the chord line and the reference plane from which the reference plane that contains the hub of our rotor. So kindly take note of those two terms. Now we have blade twist. So because of lift differential due to different rotational relative wind values along the blade should be designed with a twist to alleviate internal blade stress and distribute the lifting force more evenly along the blade. So as a recall, diba, prelim pa lang, familiar na tayo with blade twist. So, blade twist involves higher pitch angles where at the root. Then, Bakit? Kasi this is where the velocity is lowest and we have lower pitch angles naman near the tip kasi mas mabilis yung velocity there. So that's pretty much just a recall of what we discussed during our prelims. Okay? Now, another familiar term, we have the relative wind. So just for the sake of defining it, relative wind is airfoil relative to an airfoil. So it is the movement of an airfoil through the air which creates this. So just a recall. So relative wind moves in a direction which is parallel and opposite of the movement of the airfoil, as you may see sa ating photo. So ayan, nagre-recall lang tayo ng ibang terms as we try to incorporate it as we move on sa ating aerodynamics proper. Okay, now we have two kinds of relative wind. We have rotational and resultant. So ano nga ba pinagkaiba nito? So first, the rotational relative wind. The rotation of rotor blades as they turn about the mast produces ang ating rotational relative wind. Okay? So, this flows opposite the physical flight path of the airfoil, striking the blade at 90 degrees to the leading edge and parallel to the plane of rotation, as you may see there sa ating photo. So, this is constantly changing in direction during our rotation. And take note that this is highest at the blade tips. And while we talk about naman the resultant relative wind, um, the resultant relative wind at a hover is basically our rotational relative wind din natin siya. But ano naging difference? This one is affected by our induced flow. Later on, we would be introduced to the term induced flow. So this is inclined downward at some angle, as you may see, and opposite the effective flight path of the airfoil rather than the physical flight path. So it also serves as the reference plane for development of lift, drag, and total aerodynamic force or TAF vectors on our airfoil. So for further explanation ng ating relative wind, here is a video. I provided it through QR. You can scan it for further um, research. Okay, now na-mention kanina yung induced flow. So it is basic, pretty much. It is the downward flow of air through the rotor disc. So it basically happens when our helicopter redirects the air that's coming at it. And as it does, dito na papasok yung ating in-ground and out-of-ground effect. Okay, so we have IGE stands for in-ground effect and OGE stands for out-of-ground effect. So, but first, what is ground effect nga ba? So, ground effect is the increased efficiency of the rotor system, which is caused by the interference of the airflow when near the ground. So, we have here our in-ground and out-of-ground effect. So, in-ground effect, it is basically the increase in lift that occurs during hovering flights when the heli is within one rotor diameter of the surface. So, considered na nasa in-ground effect siya kapag yung distance niya at the hover is within the size of the rotor diameter or less. So, at this specific situation, we can say na mas efficient yung ating rotor blades. So, what happens during in-ground effect? Yung induced velocities natin are reduced, as you may see sa ating first photo, giving us a higher angle of attack, which requires a lesser blade pitch angle. And a reduction then in induced drag, meaning we need less power required to hover whenever we're dealing with in-ground effect. when compare naman sa ating out-of-ground effect, nawawala yung benefit na nakukuha natin sa in-ground effect when we reach a certain altitude. Now, when can we say na out-of-ground effect na tayo? So, of course, when our hover distance from the ground is lesser than our rotor diameter. So, induced flow velocity is increased, resulting in a decrease naman in our angle of attack and basically decrease ng ating lift as you may see dun sa photo. Take note sa photo na we need the higher pitch angle for out of ground effect. So, this increased pitch angle and drag requires more power to hover when it comes to out of ground effect than our IGE. Okay? So that's it. That's pretty much the difference between IGE and OGE. So there are two angles that enable a rotor disc to produce the lift required for a helicopter to fly. So these are, hold on. Yeah, angle of incidence and angle of attack. So ano nga bang difference? So angle of incidence is the angle between the chord line of the main or tail rotor blade and its rotor disc. So it is a mechanical angle rather than an aerodynamic angle and is sometimes referred to as blade pitch angle, as you can see in the photo. So in the absence of induced flow, angle of attack, and take note of this ha. Kapag wala tayong induced flow, angle of attack and angle of incidence are pretty much the same. So a change in the angle of incidence changes the angle of attack, which changes the coefficient of lift, thereby changing the lift itself. Whereas yung ating angle of attack, syempre, recall na lang to, angle between the airfoil chord line and resultant relative wind. So, compared sa ating angle of incidence, this one is an aerodynamic angle and um, it can change with no change in the blade pitch angle. So, ayun, yung pinaka-difference nila. Now that we are done with the angle comparisons, let's have the plane comparisons. We have here a figure where evident yung ating tip path plane and yung plane of rotation. So, let's differentiate lang. So, the tip path plane, by definition, is the imaginary circular plane outlined by the rotor blade's tips as they make a cycle of rotation. So, it defines the circle described by the average flight path of the blade tips in a rotor system. So, the tip path plane is most often referred to as what we call the rotor disc. Whereas yung ating plane of rotation, as you may see naman yung difference nila dun sa photo, it is the plane of the disc in comparison to our mast. So, this is changed with the what they call this cyclic movement. So, as you may see, parallel siya with our tip, tip path plane. So that is it for the basic helicopter aerodynamics. We now move forward to the forces acting on our helicopter. So we have four, basically the lift, weight, thrust, and drag. I believe na mention na ata to sa ating module before. But anyway, lift is what basically make the helicopter go up. By increasing lift, we can climb. How? By lifting our collective, syempre, and increasing the angle of attack of the main rotor blades. On the other hand naman, lowering the collective will give us slower lift, making the helicopter go down. So, yun lang yung idea ng how lift acts on the helicopter. And weight naman, weight basically opposes lift. And the process of climbing or going down depends on which among lift and weight has a greater value. And thrust, it is the force pretty much that propels the heli through the air. And like lift, it is generated by the rotation of the main rotor system. So, again, na-discuss naman na kanina yung responsibilities ng ating main rotor system, kung ano yung mga roles niya. So, in forward flight, the heli's main rotor is slightly tilted forward to generate forward thrust. And lastly, yung ating drag. So, this is the force that resists the movement of a helicopter through the air. So, drag basically opposes thrust. So, how is it created? So, by the mere, you're all familiar naman na with it. Yung contact ng air sa ating contours and yung profiles like the fuselage and stuff. Okay? So, recall na lang din, total drag is composed of three types of drag: the profile, induced, and parasitic. So, syempre, drag limits our speed kasi the more we speed up, the more drag there is. And for a heli to speed up, we need to tilt the main rotor more forward to create more thrust. And there is a certain limitation lang as to how much tilting forward can we do. Now that we're done with the forces acting sa ating heli, we now proceed to our flight conditions. So, syempre, we have powered and unpowered flight. But first, powered flight, um, in powered flight, nade-divide siya into hovering, vertical, forward, sideward, or rearward. So, a rotor's total lifting and thrust forces are perpendicular to the rotor's tip path plane or plane of rotation of the rotor. So, ito yung una na nabanggit, which is the hovering flight. So, during hovering flight, a helicopter maintains a constant position over a selected point, usually a few feet above the ground. So, most challenging part ng pagpapalipad ng heli, yung ating hovering. Bakit? Kasi constant control inputs yung and corrections yung kailangan natin from pilot. So, complex ito since it involves a number of inputs, but the inputs are pretty basic. Ang nagpapahirap lang is yung interactions and yung inputs. So, first, um, first our cyclic is used to eliminate drift in the horizontal plane. These controls forward, backward, right, and left movement. And second, yung ating throttle, if not governor controlled, is used to control revolutions per minute, RPM natin. And our collective is used to maintain syempre yung ating altitude, and yung pedals natin are used to control nose direction or heading. So, as you may see doon sa ating picture, to maintain a hover at a constant altitude, the lift must equal the weight of our helicopter. So, thrust must equal any wind and tail rotor thrust to maintain the hovering position. So, the power must be sufficient to turn the rotors and overcome the various drags and frictions involved. So, under ng ating hovering flight, we have these tendencies. So, the first one is yung ating translating tendency or drift. So, translating tendency is the movement of the helicopter to the right due to the combination of main rotor torque and tail rotor anti-torque. So, it is basically the tendency ng ating helicopter to move laterally in the direction of the tail rotor thrust. Kasi during hover for a conventional rotor, a single main rotor helicopter tends to move in the direction of ating tail rotor thrust. So, this lateral movement is called translating tendency. So, yung, as you may see sa ating photo, a tail rotor is designed to produce thrust in the direction of opposite sa ating torque. Yun yung pinaka-function niya. But the thrust produced by the tail rotor is sufficient to move the helicopter laterally. So, paano natin maka-counteract tong translating tendency or drift na ito? So, una, by applying cyclic on the opposite direction ng ating movement ng ating heli. And pwede din nating i-rig yung main rotor mass rather to the left, which would move the component of our main rotor thrust, canceling out this tendency. And lastly, we can rig din yung ating cyclic control opposite sa direction ng tail rotor thrust. So another one is the pendular action. So since the fuselage of the helicopter with the single main rotor is suspended from a single point and has considerable mass, it is free to oscillate either longitudinally or laterally in the same way as a pendulum. So this pendular action can be exaggerated by over-controlling, therefore control movements should be smooth and not exaggerated. So it is the lateral or longitudinal oscillation of our fuselage while in hover. So, this is again a problem encountered during hover. So, this is often caused by too much pilot input. Since, 'di ba, hindi agad-agad yung output na nakukuha sa input na nilalagay ni pilot. Kaya may tendency talaga na maging exage yung input. So, less ang pendulum action when it comes to rigid rotor systems kasi nga pretty much they have the quickest response time since less yung mechanisms and movements na involved. So, how do we prevent this? First, the pilot should smoothly move the controls. So, yun lang. Kasi yung pinaka-error na to nagmumula lang din naman sa exaggeration ng movements ng inputs. So, as you may see sa photo, because the helicopter's body has mass and is suspended from a single point nga, it tends to act like a pendulum. So, the next is the coning. So, coning is an upward sweeping angle of the rotor blades as a result rather of lift and centrifugal force. So, una, due siya sa centrifugal force which is created by what? The rotation ng ating rotor blades. So, it has the tendency na i-pull yung blades natin away from the hub. So, again, I believe nasa long quiz pa to nung prelim. So, yung strength ng ating centrifugal force depends on how heavy the blades are and how fast they rotate. So, result din siya ng lift. So, ano ba nagagawa ng lift? So, lift would make the blades move upward kasi nga upward component siya. So, together, itong dalawang forces na ito, as you may see in the photo, this would result in the process of coning. So now we have the Coriolis effect, so also known as law of conservation of angular momentum. So the Coriolis effect is when the rotor blades speed up or slow down as the center of gravity moves closer or further away from the axis of rotation. So take note that this is also referred to as the law of conservation of angular momentum. Recall lang tayo what does that law states. So the value of angular momentum of a rotating body does not change unless an outside force is applied. Meaning, a rotating body will have the same speed unless an outside force is applied. Same idea siya ng isang figure skater. Diba, yung speed of turn ay affected by whether their arms are extended or not. So, mas mabilis yung ikot. I don't know if you observe, pero in figure skating, di ba, they execute turns. So, mas mabilis kapag naka-inward yung arms. So, sa heli naman, there is a certain acceleration that exists when the rotor blades cone due to a maneuver. So, namumove yung ating center of gravity, same as sa skaters' inward arms. So, this acceleration is delikado since may tendency siyang mag-overspeed, and we don't want that. So how do we counteract this? So for fully article these counteractions are different sa rotor configurations natin. So for fully articulated rotor systems, we tend to incorporate a lead lag hinge. So this provides a freedom sa movement ng rotor blades which can help them. And sa semi-rigid naman, since may teeter point tayo, hindi mag-move yung center of gravity significantly. Okay, so that's it for the Coriolis effect. Now we have the gyroscopic precession. So it refers to a principle of gyroscopes that states when a force is applied to a spinning object, the maximum reaction occurs approximately 90 degrees later in the direction of rotation. So recall na lang to since we had this na for the propeller. So recall that under the principle of gyroscopes, any force is applied to a rotating object will have its maximum effect 90 degrees later in the direction of its turn. So, ayun. Recall na nga lang to. So, now that we are done with the first type of powered flight, which is the hover, now we reach the vertical flight na. So, hovering is an element of, pretty much an element of vertical flight. So, increasing the angle of incidence of the rotor blades, also known as pitch, while keeping their rotation speed constant generates additional lift and the helicopter ascends. So, decreasing the pitch causes the helicopter to descend. In a no-wind condition in which lift and thrust are less than weight and drag, the helicopter descends vertically. So if lift and thrust are greater than weight and drag, the helicopter ascends vertically. Again, our rotor is responsible for creating thrust, which is directed vertically. So this allows us to do yung vertical flight, which is not limited to hover lang. We can also do, syempre, vertical takeoff and landing. So for the forward flight naman, so in steady forward flight with no change in airspeed or vertical speed, the four forces of lift, thrust, drag, and weight must be in balance. So para makapag-forward flight, we need more lift and thrust to overcome weight and drag. So when it comes to airflow naman for forward flight, the airflows opposite of the aircraft's flight path. Sorry. So, yung velocity ng airflow na ito ay equal syempre sa forward speed ng ating heli. So, because the rotor blades turn in a circular pattern, so the velocity of airflow across the blade depends on the position of the blade in the plane of rotation at a given instant. So, its rotational velocity and airspeed of the helicopter. Meaning, yung airflow na magka-come in contact sa ating blades, they vary. They tend to vary. So, the highest velocity, since na-mention natin na it varies, so the highest velocity of airflow occurs over the right side, 3 o'clock position of the helicopter, and decreases to rotational velocity over the nose. So, it continues to decrease until the lowest velocity of airflow occurs over the left, 9 o'clock position, and increases to rotational velocity over the tail. So it continues to increase until the blade is back at the 3 o'clock position. So because, yeah, na-mention nga natin na merong certain variation na nag-exist, and as you may see dito sa photo, you are gonna be able to indicate which part um, has the higher velocity than the other ones. So, just like our hovering flight, so meron din tayong mga na-encounter during forward flight. So, isa na dito yung the symmetry of lift. So, what is the symmetry of lift? I believe na, na bigyan na kayo ng introduction regarding this sa P factor or asymmetric loading dun sa ating last na module. So, the symmetry of lift by definition is the unequal lift between advancing and retreating halves of the rotor disc caused by the different wind flow velocities across each half. So take note that the rotor blades travels with the same speed but not with the same airspeed since we have the idea of advancing and retreating side. Now, since the velocity is involved sa lift, sa formula ng ating lift, so uneven velocity results to what? Syempre, uneven lift. So, hence the idea behind our dissymmetry of lift. So, the symmetry in lift could make the helicopter uncontrollable. So, in order to counter this, we need to even out the lift of the advancing and retreating side by altering the other components of the lift formula. Particularly, the only one that we can alter, syempre, is yung lift coefficient characterized by our angle of attack. So, we can alter this through flapping ng ating main rotor blades. For forward flight, we also have translational lift, effective translational lift, and translational thrust. So, for translational lift, so lift that is gained when a helicopter translates from hover into forward flight. So, additional lift increases with increasing airspeed and is derived by the rotor system moving into undisturbed air. So, yung effective translational lift, rather naman natin, this happens due to the combination ng ating dissymmetry of lift, gyroscopic precession, and yung transverse flow effect. And lastly, yung ating translational thrust. This occurs when the tail rotor becomes more aerodynamically efficient during the transition from hover to forward flight. So recall that we only incorporate the tail rotor for anti-torque purposes. So we don't want it to be more efficient than our um, main rotor. So we also have the induced flow and transverse flow effect. So induced flow is also referred to as downwash. So it affects the rotational relative wind and has a tendency of decreasing our angle of attack. Then, syempre, affecting din our efficiency. And yung ating transverse flow effect naman, this is the rolling tendency due to lift difference of forward and aft portion of the rotor disc. So, acting as a gyroscope, so maximum effect occurs 90 degrees in the direction of our rotation. So now naman, for our sideward flight, so the tip path plane is tilted in the direction that flight is desired. So this tilts the total lift thrust vector sideward. So in this case, the vertical or lift component is still straight up and weight straight down. But the horizontal or thrust component natin, sideward na siya with drag acting to the opposite side. So, this can be a very unstable condition sa ating heli due to the parasitic drag ng ating fuselage plus yung lack ng horizontal stabilizer for the direction of flight. So, as you may see there, nagkaroon na tayo ng different components. Now we have rearward flight. So the tip path plane is tilted rearward, which in turn tilts the lift thrust vector rearward. So as you may see dun sa photo, drag now acts forward with the lift component straight up and the weight straight down. So take note that this kind of flight has hazards. So may mga kailangan tayo i-consider. since yung tail end natin, since yung tail end natin has the tendency to pitch down dahil sa position ng horizontal stabilizer, may chance na tumama to sa ground. So, syempre, yung skid design, since another thing to consider is yung skid design din. Since we want a skid design na hindi tatama sa ground during this type of flight, we need to make sure na altered siya for safety. So, we now have the turning flight. So, in forward flight, the rotor disc is tilted forward, which also tilts the total lift thrust force of the rotor disc forward. So when the helicopter naman is banked, the rotor disc is tilted sideward, resulting in lift being separated into two components. So as you may see dun sa ating photo, nagkaroon ng two components yung lift natin since nakatilt yung rotor disc natin during banking. Yung upward components which counteract yung weight is called the vertical component of lift, while yung horizontal component naman, which opposes the centrifugal force, is the horizontal component of lift, also referred to as the centripetal force. Now that we are done with our powered flight, we have the unpowered flight. Dito na papasok ang ating auto-rotation. So, auto-rotation is the state of flight where the main rotor disc of a helicopter is being turned by the action of air moving up through the rotor rather than the engine power driving the rotor. So, compared to a normal flight where air is drawn into the main rotor system from above, then is being exhausted downward. Sa auto-rotation, yung air natin would be coming from below that would move up sa ating rotor system as it descends. So, babalikan natin yung freewheeling unit which allows the main rotor to continue turning kahit di na gumagana yung engine. This happens by disengaging the engine from the main rotor. So, this makes the process of safe landing possible kapag may engine failure. So, take note that all helicopters should have this capability bago siya ma-certify. So, during vertical auto-rotation, the rotor's disc is divided into three regions, namely yung driven region, driving region, and stall region. So, to get that into detail, here's it. So, as you may see in the photo, part E is the driven region. B and D are points of equilibrium. Part C is the driving region, and yung stall region naman natin is yung part E. So, the driven region is also called the propeller region, and ito yung nearest sa ating blade tips. So, normally, it consists of about 30% of our regions. So, in the driven region, the total aerodynamic force acts behind the axis of rotation. So, this will result in an overall drag force. So, yung ating drag region naman, driving region, is also called the autorotative region. So, this normally lies between 25 to 70% of the blade radius. This produces the force needed to turn the blades during auto-rotation. So, the total aerodynamic force in the driving region is inclined slightly forward of the axis of rotation. So, this produces a continual acceleration force. And lastly, yung ating stall region, which can be found sa ating inner 25% of the rotor blade. This operates above its maximum stall angle, so which causes drag, so which tends to slow rotation ng ating blade. And that is it for our helicopter flight conditions. So we now move to momentum theory. So we discussed momentum theory naman na for propellers. So, I guess this would just be, we would just be having a pretty short recall than the application proper. So, as I've told you, we would be having a short recall. So, isa to sa mga kailangan nating i-recalls since application, gagamitin natin siya sa application later. So, the variable systems of particles. So, engineering applications like hydraulic turbine, rocket engine, and more require the consideration of variable systems of particles. So, you should all be well versed of this. Recall na lang siya from your Mech 323. I believe module 5 niya yata yun. System of particles. Yeah, if you wish to have a refresher, you can do so. So, included siya sa ating recall yung steady stream of particles. So, the first one, mass flow rate is constant in the system. So, mass flow rate is the difference of mass with respect to time. So, force is equal to the mass flow rate and change in velocity. Where, as you can see then, yung Fx, which it is the net external force sa body. And yung VREL is the relative velocity ng ating relative velocity of the escaping or incoming mass with respect to our center of mass. So, again, under pa din ng recall natin from Mech 323 is yung streams gaining or mass accretion. So, a body of time varying mass m moves at a velocity v at an initial time t. So, in the same instant, a particle of mass dm moves with velocity u with respect to ground. So, the initial momentum can be written as yung ating nasa first bullet. So, now, at the time t plus dt, let both the main body and the particle accreted, accreted into a body of velocity v plus dv. Thus, the new momentum of the system can be written as yung ating second bullet. Then, we get the difference in P by equating P1 and P2. Then we simplify it to the further bullets. Then we would be applying the second Newton's second law, which states that force is equal to mass multiplied by acceleration. So note that u minus v is the velocity of dm relative to m. So this is symbolized as again vrel. This final equation can be arranged as you may see dun sa ating final equation right there. So again, this would just be pretty much a recall for you. So we reached the momentum theory na. So I gave naman the um, assumptions of momentum theory during our prelim, but um, just a recall again. Momentum theory is also known as the disk actuator theory. So, the helicopter rotor can be idealized as a momentum disk. It imparts a uniform velocity, which is denoted by VI, to the airflow, creating a change in momentum, which will result in an upward thrust. So, of course, friction is not included. So, we would be applying this to certain pieces of flight. So, una is yung ating hover. So, for the hover case, air is sucked in from all directions so that Fairfield inlet velocity is effectively zero. So accelerated to VI at the disk and propelled to a final slipstream velocity of Vs below, as you may see in our photo. So ito yung pinaka-application na natin sa kanya. So equation 1, recall that for equation 1, if the area at the disk is A, so our mass flow being accelerated is denoted by rho AVI. And for the second equation, so change in momentum of the disk is denoted as mass flow rate multiplied by our Vs. And next, equation 3, since thrust is defined as the rate of change in of momentum opposite uh, within the direction opposite to the direction of motion, we can say na thrust is equal to rho AVI multiplied by Vs. So that is our equation 3. So, ang equation 4 naman natin, take note of this, pretty much our mother equations para maging easy yung ating derivation. So, for equation number 4, recall that, recall lang siya ng change in kinetic energy formula. So, we have 1 half mass flow rate multiplied by our Vs squared. And our equation number 5, another recall for the formula for the work done per unit time. So we have W is equal to TVI. So recall that the total work done by all the forces acting on the particle or the work of the resultant force is equivalent to the change in kinetic energy of a particle. So since W is equal to delta E and W is equal to TVI according to our equation 5, substitute T from equation 3 and the energy equation from equation 4, we would be having this, and further simplifying, we would be having Vs is equal to twice our Vi, which will serve as our equation 6. So from equation 3 and 6, which is this, we would be having T. Then, since T should be equal to our weight, we can say na Vi is equal to the square root of T, which is equal to weight, over 2 rho A. So, this is just basic derivation since provided naman na yung mga mother equation na kailangan natin. Okay. So now that we are done with hover, we proceed to climb. So for the case where the helicopter is climbing, the rotor will capture flow from a fixed area above and accelerate this to a final slipstream velocity. So the momentum balance will be slightly different as the incoming air has an initial momentum due to the helicopter climb speed and of course yung the rotor. So the variation of pressure will drop below atmospheric, above the disk increase due to the energy input of the disk, and then drop back to atmospheric in the slipstream. So here is nauna yung mga box. So yeah, hindi ko naayos yung transition properly. Sorry. So, same process of the derivation as the hover, but this time, given that the momentum balance is expected to be different, mag-iba yung ating flow rate. Pero everything else, the process is just the same. Okay? So, as you may see there, So, equation 1 pa lang natin is nag-iba na siya. So, that is the mean difference sa ating hover and climb. But again, yung process of derivation would be the same. So yeah, I won't be discussing this in a manner na would make our recording long enough, ano, since basic, yung sa derivation, algebra lang siya, wala naman tayong algebra and konting diffcal. So, I think, magigets nyo naman na yun. So, we now reached our momentum theory, which deals with descent. So descent can be analyzed by using a negative value of Vc in the above equation. So however, there are physical limits on this approach due to the changing flow pattern. So you will notice later on sa figures na ang capture area natin is now below. So what happens? So the rotor is now pretty much recirculating its own wake to create momentum change. So there will come a point na since nire-recycle na lang ng ating rotor yung sarili niyang wake, wala na tayong magiging change in momentum. And as we defined thrust a while ago, thrust is coming from the change in momentum. So no change in momentum means no thrust. So we have here for descent, slowly descending rotor. So thrust is positive. As you may notice, same lang siya sa climb since thrust is again positive pa din. And yung sa ating statement kanina, the capture area is below, as you may see. So, take note na for no thrust, as you may see in the photo, so vortices na lang siya. So, na-discuss kanina na at some point, while the rotor tries to recirculate its own wake, there would come a time na wala na tayong magiging change in momentum, hence no thrust. So, that's why for moderately descending rotor, here's the equation na zero siya, which is no thrust. So, yeah. So, here is naman yung for our fast descending rotor or windmilling. So, never mind yung sa first na no thrust. I think, hindi ko lang na-edit na maayos. Pero, yung um, dalawang equations. So, capture area is still below, but rotor is absorbing momentum from the stream and a divergent slipstream appears above. As you may see there, yung slipstream natin nasa taas na. So, this negative change in momentum will again produce a thrust or a vertical drag. So, this flow state can be used for auto-rotation ng ating blades. So now we reach the power required. So I need you to take note of these formulas for power required. So engine power is required to be supplied to the disk in order to produce the required thrust, syempre. So power is required to produce the momentum change and power is required to make the helicopter climb. So kindly take note of these power required formulas. Okay, so neglecting power losses in transmission, fuselage drag components, blade profile, drag power, and etc. So the power required for the operation of the rotor would be this one. So take note of what we neglect and what we signify. So I would just be briefly discussing a recall of the figure of merit. So the figure of merit accounts for the aerodynamic efficiency of our rotor. So it is um, we can get the figure of merit by dividing the ideal power required to hover divided by the actual power required to hover. So, bakit ko to sinama sa discussion? Kasi we would be using this one sa ating problem solving. So, let's proceed with our first sample problem. Okay, so sample problem. So a tilt-rotor aircraft has a gross weight of 60,500 pounds. So the rotor diameter is 38 feet. On the basis of momentum theory, estimate the power required for the aircraft to hover at sea level on a standard day. So assume that the figure of merit of the rotor is 0.75 and the transmission losses amounts to 5%. So as engineering practice, let's state our given. So first, um, we have T, which is yung gross weight ng ating um, rotor divided by, syempre, yung two blades natin, which we can get 30,250 pounds. So, our diameter, which is 38 feet, our figure of merit, which is 0.75, and our transmission loss, which is 5%. So, now we can proceed to our solution. So, step 1, we have to get the area using, syempre, yung ating diameter, which is 38 feet. So, to get that, we syempre apply the formula given na alam natin na yung shape ng ating rotor for momentum theory is assumed as a disk. So, the area is 1,134.12 square feet. So, our second step now is to get the induced velocity. So, you would be getting it by na-state naman kung anong phase siya. So, we have our formula for VI, which is the square root of T over 2 rho A. So, direct substitution lang to since we have our T na. We have our density since stated na standard sea level to, so SSLC. Then, syempre, our area. By then, we would be getting 74.888 foot per second. And our next step is to get the ideal power from where? From our formula of P is equal to TVI. So we have our T, which is 30,250 pounds, multiplied by our induced velocity, which is 74.888. And we would be getting 4,118.8403. So, take note na for this one, always convert to horsepower. So, for step 4, get the actual power from the figure of merit. So, I gave you a while ago the formula for figure of merit. So, it is ideal power, power required over actual power required. So, since we have our ideal power, we would be able to get the actual power required. Then, we would be multiplying it by 1.05 for the transmission losses. So, we have to take into account the 5% ng transmission loss natin, which would give us the final answer of 11,532.7528 horsepower. So, yeah, this is pretty much, this is multi-step, but the steps are pretty much simple. You just apply the basic principles that we tackled. So that's it for the momentum theory. So now we would just be discussing briefly about the rotorcraft flight manual. So the production of performance charts and diagrams for helicopters are regulatory, as set out in the Title 14 of the Code of Federal Regulations. Part 27, Airworthiness Standards. So, pretty much, I would just be disclosing kung ano yung mga under ng each sections, from section 1 all the way to section 10. So, section 1 includes general information, section 2 includes the operating limitations, section 3 includes the emergency procedures, section 4 includes the normal procedures, section 5 the performance, section 6 is weight and balance, section 7 is aircraft and systems description, section 8 is handling, servicing, and maintenance, and Section 9 is supplements. And lastly, Section 10 is safety and operational tips. So kindly take note on um, these sections. So that's it for the rotorcraft flight manual. We now move forward to the helicopter performance. So first, we would discuss the factors affecting performance. So the first one is moisture, of course, humidity, density. So decrease in hovering and takeoff performance in high humidity conditions, syempre. Tapos, we have the weight. So at higher gross weights, the increased power required to hover produces more torque, which means more anti-torque thrust is required. So, lastly is yung winds or velocity. So, takeoff and climb performance is greatly affected by wind translational lift increases. So, this results in less power required to hover. Increased tail rotor thrust absorbs power from the engine. So, which means there is less power available to the main rotor to produce lift. So we now have the performance charts. We have five. We will be focusing more on the four. So I will be showing pictures and explaining one each in detail. Okay, so we now have the height velocity diagram or HV diagram. Okay, sorry. So HV diagram shows the combinations of the airspeed and height needed to complete a landing after an engine failure. Basically, the shaded regions should be avoided by the pilot since there is a possibility that a safe authorization rotation cannot be done during those operations under that shaded region. So for the gross weight versus altitude chart naman, here is the photo for a while. Okay. So gross weight versus altitude chart. This chart serves as an advisory of the auto-rotative capability of the helicopter during takeoff and climb. So we now have the auto-rotational performance chart as seen in the photo. This shows the various combinations of horizontal and vertical speeds that supply the required energy to keep the rotor turning at a constant RPM. So now the hovering performance chart. So these are provided for in-ground effect, hover, and out-of-ground effect, hover, under various conditions of gross weight, altitude, temperature, and power. And lastly, I don't have a photo, sadly, of the climb performance chart. So this shows the change in torque above or below torque required for level flight under the same gross weight and atmospheric conditions to obtain a given rate of climb or descent. So to further understand, here is a sample hover problem. So using the figure here, determine what torque is required to hover. So, using the following conditions. So, we have the pressure altitude to be 9,500 feet, the outside air temperature to be 0 degrees Celsius, and our gross weight to be 4,250 pounds, and our desired skid height to be 5 foot. So, what should we do ba? So, here is a more zoomed version of the photo. So first, enter the chart at 9,500 feet pressure altitude, since yun yung given natin. Then move right to outside air temperature, which is yung given din natin, 0 degrees Celsius. Then from that point, move down to 4,250 pounds gross weight, given natin. Then move left to 5 foot skid height. So drop down to read the 66% torque required to hover. And that's pretty much it. So again, take note of this since I think hindi nyo masyadong naaral yung mga graphs natin for the prelim, and that pretty much leads to failure ng ibang students when it comes to the exam and the long quiz. So yeah, kindly take note of this one. And lastly, we have the helicopter 3 views. So orthographic projection, there are 6 possible views of an object because all objects have 6 sides. So the front, top, bottom, rear, side, and left side. So it is seldom necessary to show all 6 views to portray an object clearly. Therefore, only those views necessary to illustrate the required characteristics of that certain object are drawn. So, um, 1, 2, and 3 view drawings are the most common, specifically yung top, front, at side. So, bakit to diniscuss? Kasi, eto, dito na tayo sa assessments and announcements. Kaya ako diniscuss yun briefly. Pretty much, recall lang yun. Kasi syempre sa drawing nyo, you should all be well versed with that na. So, we have um, mastery checks for Module 4. I would be posting it naman. And I would be indicating which of the mastery checks you would be answering. And just use our old format. And we would be having technical reports, specifically yung helicopter preliminary specifications and helicopter reviews. So just like last time, hopefully I would be able to record a guide ng instructions para mas madali nyo siyang magagawa. Pero if not, I would be providing naman a guide in PDF or Word format para mas madali. Pero, yeah, consult na lang yung ating um, deadline matrix for you to expect what date. Pero, again, tentative pa yon, so pwede pa natin siyang i-adjust further. Pero, so far, yun yung pinaka-ideal sa ating schedule since exam, with respect sa ating exam week, syempre. So, para meron pa tayong time to check and, syempre, to avoid what happened last time na hindi ako nakapagpa-repeat ng activities due to um, the lack of time. So just kindly expect these activities and lab reports to come your way. I would be posting it ahead of time naman sa ating Google Classroom. Um, I will be giving you much time to um, finish these. So that is the end of the presentation. So thank you for watching, and yeah, I hope you learned something. So um for further like research, I encourage you actually to read the modules, not just the modules, the links of the books ng reference ng modules, the links of the videos together with the modules. So that is important kasi yeah, pretty much coverage din siya. Pero as much as we can, we try to stick with what is in the recording and what is in the module to get the exam and the quizzes. So that is it. Thank you.